Okay, so let's start with the supplemental part. In supplemental part 1 is needed to compute the pseudo-density of the base and the tail part. And, well, what we need here is the following lemma. So, let x be a random variable with piecewise continuous Lebesgue density f. And r is still our cutoff parameter. So r is greater than 0. And then we have the following. So the conditional distribution of x under the condition x greater or equal than r, while has a Lebesgue density, and the Lebesgue density is given by a constant c1, the normalizing constant, the indicator function from r to infinity times the original Lebesgue density. And well, also for the opposite condition we have the same statement. So we have again a Lebesgue density, different normalization constant, and of course the indicator function now for the complement set. So it's now an indicator function from minus infinity to r times the original Lebesgue density. So we are getting the new densities from the old densities by this normalizing constant, and then the indicator functions for the respective conditions. So from r to infinity for greater or equal than r, minus infinity to r for less than r. And what are the normalizing constants? Well, the normalizing constants are as follows. Well, they're just the normalizing constants. C1 is 1 divided by the probability that x takes values greater or equal than r, and C2, 1 is 1 over the probability that x takes values less than r. Okay, how to prove this? And well, we will only prove 1 here, 2 is completely analogous. And how to derive densities? Well, one way is to compute the distribution function and to differentiate them. So let's do this here. So we have g of z, where g of z is the distribution function of the conditional distribution of x under the condition x greater or equal than r. So we need to look at these probabilities here. So we need to take the probability, the conditional probability for the when that we take values between minus infinity and z. And by definition, well, this is just this fraction here, so x less or equal than z and greater or equal than r, the joint event, and we divide it by the probability that x is greater or equal than r. Okay, and first thing what we see, well, this is just C1, by definition of C1 times the probability of x less or equal than z, x greater or equal than r. Okay, and now we have two cases. Why? Well, if z is less than r, then, well, we have conflicting conditions. So we have the empty set as you went, and so we have probability 0 if z is less or equal than r. And, well, in the other case, well, there we can just exploit the density. So x is greater or equal than r, and x is less or equal than z. So this is just the integral from r to z fy dy for z greater than r. Okay, and now we are almost done. So for z not equal to r, we can now differentiate, and we have the following. So the density of the conditional distribution, well, is z not equal to r given by the derivative of the distribution function with respect to z, and well, if we differentiate 0, we still have 0. And in the other case, well, we differentiate an integral with z as an upper bound with respect to z. So we are just getting z1 times f of z for z greater or equal than r. And here I see also c1 missing. Okay, and so we're actually done. While we are done, so while z not equal to r is missing, but for a density 1 point just doesn't matter, and we can define the density in this point as we want. And part 2, as I said, is completely analogous. So that finishes supplemental part 1.